Hello, greetings. You hear me? So I would like to start. My name is Khrystyna Levchenko, and I am very, very excited to be here. And for this possibility, I would like to thank the organizers. I am also very excited to present you not one, but actually two interesting topics today. So the first one is actually the one that you see in the abstract book, and this is connected with dilute magnetic semiconductor, so the area of spintronics. Second part of my topic will be a transition to a new field of ferromagnetic magnonics. So let us start. As I already mentioned, my first part is dedicated to dilute magnetic semiconductors, and all investigations I'll be showing in it were performed in Institute of Physics, Polish Academy of Sciences, as a part of the group of Professor Tadeusz Wyszyński. And I'm very excited and I'm very grateful for all the people who supported me in their corresponding fields of expertise, as you may see on this slide. Just maybe briefly, I will come back so you will see the title of my slide and word of appreciation. So this is the first part of my talk. This is the second part of my talk. Dedicated to magnonics, the first one to spintronics. These are all collaborators during my PhD, and I obtained results that I'll be showing today in the first part, together with a group of Professor Tadeusz Wyszyński. And, of course, our driving force was to go beyond electronics. As we are known that Moore's law, where, for example, we have the decrease the size and price of a transistor and increase of efficiency, is running up to its course. For example, on this slide, you see the roadmap of the transistors was given by Intel and IBM. Of course, they were improving material. They were searching for different architectures, but up till today, there is more and more accent and highlights on the new material which will give us the best long-term results. And 3,5 gallium arsenide was one of those. So, but what if we add manganese to this? We will get a dilute magnetic semiconductor, gallium manganese arsenide. It's a ferromagnet where the exchange interaction is driven behind the interaction of manganese 3D moments and delocalized charge carriers. It's an interesting material, there are already a lot of different concept devices created on it. But we decided to go even further, as the material was boomed into investigations in the mid-90s. And this is a novel thing. We added one of the heaviest stable elements of the fifth group, which is bismuth. And before proceeding further to characterization, I would like just to introduce you briefly what type of films we did have. All the transport measurements were performed on the 10 nanometer thick films with a concentration of manganese 6% and bismuth around 1%. Samples were grown with the means of low-temperature molecular beam epitaxy on a gallium arsenide substrate. Hence, we have a comprehensive, compressive biaxial strain and in-plane anisotropy. We'll be working only with the left case, not with the tensile one, today. Before proceeding to magnetotransport, I would like to prove that all our samples were of high quality, and for this you see the results from the SEM, mass spectroscopy, and high-resolution X-ray diffraction reciprocal lattice maps. The SEM shows no defects in the vicinity. The scale is 10 nanometer for both the ternary and quaternary compounds. The ternary is on top, the quaternary is on the bottom. Also, SEMS showed that we have a signal from manganese and bismuth throughout the first 50 nanometers where it's supposed to be, while gallium arsenide throughout all the layers. And reciprocal lattice maps show that we have a nice strong peaks from the substrate and layer. Hence, in the end, we can say all our samples have good crystalline quality. We can proceed further to characterization. So this is a typical view of our sample. We performed our measurements on the whole bar shaped samples, whole bar configuration of the contacts. So in this occasion we had contacted them manually with the indium, and the sample was put on the chip and connected with the golden wires. Then we could, for example, put our chip inside the magnetic coil, which is connected to the contact's output in the measurement setup, as you may see. And then we connect corresponding contacts to lock-ins through preamplifiers and collect our signal. Obviously, we had different chips, so we can, for example, change the angle of our sample. In this case, the field was applied, of course, along the long side. Current, obviously, was measured behind these contacts, and as is the whole configuration. And when the sample is fully saturated, the magnetization is also along the field direction. What we measure it, if we, for example, measure along the transfer pair of contacts, the phenomena will be planar Hall effect phenomena, which is described by the first equation in the box. So it's a spontaneous transfer voltage in response to longitudinal current when we apply our magnetic field in plane, sometimes even in the absence of it. And when we measure between the contacts in longitudinal direction, then we see the anisotropic magnetoresistance. It's a magnetic field dependent response, as you already noticed, and everything in our resistance depends on the angle theta between magnetization and current. Both origins of this effect lie in spin-orbit coupling. Here you see how we were measuring. So everything was performed in 4.2 Kelvin liquid helium temperature. We start with a sweeping magnetic field to plus 950 Erstat minus 950 Erstat, and immediately the planar Hall measurement show us 4 extremum points. The explanation of them we see as magnetization is reoriented while we are sweeping magnetic field, corresponding to 4 extremas. Its theta equal to 45 in this equation, and its cubic equivalent. Also, I would like to point your attention that the graph is very nice and symmetric, and the reorientation is running throughout the whole easy axis, because it's easy in plane magnetization. We start with 0, minus 1, 0, and we go throughout whole 360 and come back to 0, minus 1, 0 at this point in the field. At 550 Erstat, in this case, we also we have something which we coined as recurrence point, below which these effects of reorientation are suppressed by strong enough field. So we have a negative magnetoresistance. And not only for the planar Hall effect, same was observed for the magnetoresistance, as you may see here, but I would like to point your attention to the fact that both of those curves, they have the same, basically the same phenomena are driving them, the same shape, but the magnitude is increased, coercive and anisotropic fluids are increased, which means that in a case when we add 1% of bismuth, we still have the same spin-orbit driven phenomena, but adding a heavy material, we are enhancing them. So this is a qualitative characterization. We would like to quantify it. And in order to do that, we decided to apply weak localization quantum correction to conductivity. To perform that, we applied our high magnetic field perpendicular in this case. You see another interesting combination of Hall effect presence. So in lower fields, when the field is applied perpendicular, we see the anomalous Hall effect or the contribution of magnetization. But then when we reach high enough fields, there is a classical behavior from which we can characterize our carriers, the holes, and their concentration, which was 2 times 10 to the power 20. And then in magnetoresistance, we actually have a combination of 3 interesting phenomena. So in the lower fields, below 0.4 Tesla, I would guess, we do have our positive magnetoresistance. So this reorientation. Then we have the combination of weak localization and weak anti-localization. And then if we reach strong enough fields, we didn't, we will probably observe the classical linear Boltzmann behavior. But for this, we would like just to concentrate on the middle segment, so these, to characterize weak localization and anti-localization, which are both phenomena connected that when the charge carrier is propagating, it's going up through self-intersecting passes. And depending whether you have constructive or destructive interference, you will have either addition or reduction of your resistance, which is basically the weak localization. And it's classical for materials with a high disorder, or generally with a disorder, or driven by spin-orbit coupling. And we measured this in 4.2 and 1.6 Kelvin. As you may see, both our ternary and quaternary compounds. The experimental data, it's open circles, while the red line is fit data. And the equation that we used to make this very nice fit is presented here. It's a weak localization correction to semi-classical Boltzmann model. As you may see, it's equation correction to the conductivity based on the d gamma function. And in the d gamma function, Dugaev, Barnas, and Brno, which are the authors, introduced something like 3 different parts of the field. So it's a field corresponding to propagation with the elastic scattering, which is BP, inelastic, which is Bphi, and spin orbit. Both they are all of them are depending on the mean free length specifically for these regimes. And the end result was for spin orbit, because that's what we're interested in. We have a twice reduction in comparison, twice reduction of LSO in the case of gallium manganese bismuth arsenide comparing to gallium manganese arsenide. Less propagation distance, or less distance where S or interaction plays a role, means there is stronger interaction. Means we have 200% increase of spin-orbit coupling. And just to show that it's not only weak localization, we decided to, for example, tune our model. We set LSO to infinity, meaning we have basically no spin-orbit coupling, and spin-orbit coupling is contributing to weak anti-localization again. And immediately we saw the sharp blue peak, which is 10 times higher than actually what we observed in real experiments. And the red peak fits very nicely with experimental data. Hence, it's strong interplay between these effects. And I would say that was a very interesting and exciting results. This is a conclusion to the first part. We measured, I think, one of the first magnetotransport in sub 50 nanometers, in 10 nanometers thick quaternary compounds of high quality. We observe increase of spin-orbit coupling qualitatively through magnetotransport and quantitatively through the characterization with a weak localization correction to conductivity. This was very interesting and exciting work on a spintronic material. And now I'm a part of a new group. I'm doing my postdoc in University of Vienna in a group of nanomagnetism and magnonics. And all these great people, as you see here, some even familiar faces are in this room. The group leader is Professor Andrei Chumak, and he will give talk a little bit later in the conference. And we had also some awesome results that were presented by Professor Dobrovolsky, head of a super spin lab. But we also do have a lot of amazing collaborators. For example, we are working with Kaiserslautern together on the BLS measurements and spin transport measurements. With IMAC, in SATEC, for example, we do a lot of fabrication, nanofabrication, and very unique measurements in this research center. Very strong, as you already heard today, theory is provided by Ukraine in different institutes in Kyiv, and sample of exceptional quality were grown in Innovent in Vienna by Dr. Dubs. And of course, last but not least, is a very known in University of Vienna group of Professor Dieter Zeus, with whom we also do a lot of collaborations. And also you see Ms. Budinska and Mr. Carlton today. They're also going to give us talks. So if you're interested in experiments or low temperature superconductivity, follow them.
You have 3 minutes.
Oh, yes, I will try to tell you something meaningful throughout these 3 minutes. So I might skip an introduction to yttrium, iron, and garnet, because today it was very nice given. You already heard about the Bose-Einstein condensate like of the magnons, and of course this is amazing material with the narrowest known ferromagnetic resonant lines and lowest spin wave damping. There are a lot of concepts, for example, a directional coupler, which was done by Dr. Chi Wang, and if you're interested and would like to read more, please visit those papers. But again, we decided to do something more. So if we add to our high crystalline quality material that we can grow very thin, sub 100 nanometer, with the smallest magnetic loss, some diamagnetic material like gallium. Well, of course, you will decrease your magnetization. As you may see with the, I hope you see, as you see with the, actually in this work from 70s with increase of the concentration of gallium, which is substitute iron in this ferrimagnet, we are decreasing 9 times our magnetization with the 1% of gallium. Also, we are decreasing the transition temperature. So with a strong enough concentration of gallium, we would be able to reach an anti-ferromagnetic state. But why would like to do that? It's a there is a lot of focus to this class of materials lately because they give you no stray fields. They have large anisotropies and can bring your original in-plane for YIG magnetization direction to out of plane, which will be preferable for a practical application. And of course, the room temperature application is also a key and focus point in this research. But why it wasn't realized up to date? Well, in this old article, and for a long time, there was no breakthrough because it was a micrometer thick material. And with the latest results that were obtained amazingly by Dr. Dupes, we are able to have materials down to 10 nanometer thickness. And this is the focus of the current project of functional layers of nanometer thick geek films, which is between three research groups, Jena, where the Dr. Dupes is grabbing our samples, then Khrystyna, where there is a BLS characterization, a spin transport characterization, and us, where we perform FMR and also partially the BLS characterizations. So today, I hope I will give you like a small peek to what is FMR characterization and why we need to do it now with our material. So we want to have, before proceeding to propagating wave, we want to have our Gilbert damping value in this novel material. We also do want to have a proof that we have out-of-plane magnetization and some anisotropy values. And this was performed on the FMR VNA setup, vector network analyzer, ferromagnetic resonance spectroscopy setup in University of Vienna in our lab. By measuring and obtaining, for example, a resonance frequency as a function of applied magnetic field, just naively fitting with the Kittel equation for the in-plane, what we see, well, believe me, what you will see is negative effective magnetization. What does this mean? Effective magnetization is hiding saturation magnetization and anisotropy terms. Originally for YIG they are as small and 30 for uniaxial and 50 for cubic. Here it means that these anisotropies are so high that they are overshadowing our saturation magnetization. Hence, a stronger theory is required to describe our materials. And indeed, we find such a theory. It's a group from Professor Zavislak from Kyiv, where you see the equation which depends on the anisotropy ansatz for the in-plane, in-plane and out-of-plane. And for both in-plane and out-of-plane, these anisotropy ansatz, they depend on the crystallographic orientation of the substrate. So if you have GGG 100, 111, or 110, and how you apply your magnetic field in a case of in-plane characterization. So substituting with these anisotropy ansatz terms, I can show you later if you're interested. I have a more precise analysis. We are arriving to this set of equations. So for the GGG 111, now we're looking at the cubic anisotropy, uniaxial of the first order for the in-plane, and for the second order for the out-of-plane. We are able to, having this set of equations, to fully characterize our material. And in the case of material on GGG 100, the same. Also pay attention that these equations, the bottom one, are different from the top one. And in the end, if you do not do carefully a characterization, you will get very different results, and you will not get the proper Gilbert damping, you will not get your proper fields or saturation magnetization. And these are results. First, well, as you see, it's ongoing work, so some gaps will be filled. First of all, the reference YIG, usually typical value, 1,800 Ørsted. But with 1% of gallium, around 1% of gallium, we already seen a 9-time reduction of saturation magnetization. It's already 200. While the uniaxial one, which was 30, now it's around 900 or even 1,000 Gauss. At the same time, pay attention that Gilbert damping, well, it's increased, but still it's very good value. It's still in the order of 10 to minus 4. And I think that will mean that when we will fully saturate our materials, we still will have materials of good quality that can be further investigated as a potential candidate for magnonic applications. And with this, I would like to thank you for your attention, and I'm open for questions.
Okay. Congratulations. This is your certificate.
Yeah. Thank you.